All right. Okay, so let's continue the story of unexpected, expected things that could show up at High Lumi. So I'm giving you 3 examples of things that could show up. I don't have any strong theoretical motivation for why they should show up, but there's no reason that they shouldn't. And so I'm just giving you these examples and trying to illustrate in each one, you know, how these naive scaling arguments can help you understand better or estimate better what the prospects are. Yes, thanks. It'll be figure 1 in about 10 minutes, I think. Okay, so the next example is the Higgs self-coupling. Okay, so first I want to discuss a little bit, I'm going to be quite quick in this section, a little bit what the experimental status is, what it will be, and what the theoretical status is. So I've heard the Higgs self-coupling is very difficult to measure. We'll discuss why in a second. And I've heard it referred to in the past as the sort of the white whale of particle physics, in the sense that it's something many theorists have thought about, ways to try and measure it, and many experimentalists have worked very, very hard on trying to optimize analyses to try and measure it, because in some sense, it's one of the last remaining parameters of the standard model. It's not the absolute last, there's the Higgs quartic, but it's one of the last ones that is very important and we wish to measure experimentally. So who's familiar with, just to get a sense of how quick I should go, who's familiar with Higgs self-coupling measurements at the LHC and how you do it? No? Okay, excellent, right. So, it's sort of, yeah, okay, so you measure the main way for accessing the Higgs self-coupling at the LHC is through gluon fusion, so the same initial state as drives Higgs production at the LHC. So you have gluon fusion through TOPS. This is a top loop, plus this diagram here. You have the Higgs self-coupling in here, and an off-shell Higgs here. So these 2 diagrams contribute to Higgs pair production at the LHC, and they actually interfere. And the Higgs self-coupling only enters here. So what that means is that unlike, you know, the rate, for instance, for the Higgs decay to muons, that was going like the Higgs-Yukawa coupling squared. This is different. You've got an interference pattern, so this is like a polynomial. You've got some constant piece plus something times the Higgs self-coupling plus something times the Higgs self-coupling squared by the time that you have squared these production diagrams. Now, the Higgs self-coupling, now that we've measured the Higgs VEV and the Higgs mass, the Higgs self-coupling is predicted in the standard model. So we know what the standard model value is. If we hadn't measured the Higgs mass, we wouldn't know. That doesn't mean we don't want to measure it. It's just like everything. The Higgs coupling to Zs is predicted, to photons. Everything is predicted in the standard model at present. But the reason we measure it is that particle physics is an experimental science. So we actually want to know for sure what's going on. And so, because it's predicted in the standard model, we can compare present determinations to the standard model value. And presently, the uncertainty on the Higgs self-coupling is around, I'll call it delta lambda h cubed. Any guesses? Just order of magnitude, ballpark it. You don't have to get it. There's no wrong answer here. How well we know it. If you think the Higgs muon, Yukawa, we're starting to probe at like the 25% level. If you recall, and that's a tiny, tiny coupling. So does anyone have any ideas for how well we can probe the Higgs self-coupling? Yep.
The K factor is around 5, 6 or something?
Right, exactly. So the K factor is around 5 or 6. In fact, the central value is quite high. So the uncertainty is around the 190% level. The central value is quite high. So it's sort of like 3 plus or minus 200% at present. Yep.
Lambda is the coupling for both triple and
No, they have different dimensions. So the self-coupling comes from the Higgs potential. And so this in unitary gauge, right, you've got over 8, you've got 2hv plus h squared. And the triple coupling comes from the cross term here, so you've got lambda times 4v from that cross term, and the Higgs quartic, you've just got lambda.
So when you're saying that lambda is the coupling force of that vertex, it's not actually lambda, but lambda.
No, it's not that. I'm just any parameter. Let's call it whatever, A.
It's not the lambda from the Lagrange.
No, yeah. No. Okay, so yeah, let's just, I want to keep it the same notation. I was calling it, sorry, lambda h cubed. Lambda h cubed. So the uncertainty is about 200%. Yep.
Sorry, it's a question, but how does uncertainty arise? You're basically saying we can determine this coupling up to this precision in
Yeah.
some sense at the moment.
Yes.
How do we do it?
So that's a great question. So, keep doing that. Okay, so the cross, let's call it the cross section, but this is like after cuts, you know, selecting for final states, all that sort of stuff, is like sigma, the standard model cross section for Higgs pair production, times 1 plus some constant. I don't know. I don't know off the top of my head what it is. I'll call it my unknown constant A again. A delta lambda Higgs cubed plus B delta lambda Higgs cubed squared. Okay, so if delta lambda, and this is like the ratio, delta lambda is the ratio of, if we say the true value, lambda h cubed over lambda h cubed, the standard model value, is 1 plus delta lambda h cubed. Okay, so if delta lambda is 0, it's just the standard model value, and you get the standard model cross-section. So with experiment, you measure the rate of Higgs pair production in some final state, usually something like BB gamma gamma is one of the best. And you compare the cross-section that you get relative to the standard model. And so if you got exactly standard model-like, you'd get that cross-section plus or minus some error bar, which corresponds to varying how big or small delta lambda could be. So it's from essentially the uncertainty on the measurement is one way to think about it. Or if you were being more sophisticated, you would say that the likelihood function is a function of delta lambda, and you take it the likelihood to your, 95% to get, sort of 2 sigma, even though it's not necessarily pure Gaussian. But I'm a sloppy theorist, so I'm being a bit basic about things. Okay, so the error is around 200%. The central value is a bit high. So assuming that that it is the standard model, and so that this central value being a little bit high is just a fluctuation, then we can estimate how well we will measure it at high Lumi. Now I'm going to do my stupid estimation again, so my dumb one. Delta lambda h cubed at high Lumi should be of order 190% times, again, just the ratio of square root luminosity, assuming that this is, assuming 0 systematics, right? And assuming that this is a final state with large standard model background. You would expect in the future that you would get something like 140 over 3000. Again, this factor of square root 20, as before. And so my naive estimate is 40%. Thankfully, some experimentalists have done a serious job of estimating how well we can do at high Lumi, and it's actually about 50%. So these are the projections for the uncertainty on the Higgs self-coupling at high Lumi. This is my naive one. I think it's pretty good. And in fact, I would bet more on this one because there's, as Michelangelo Mangano said, there's a people factor and things get better as more and more people turn their attention to an analysis. Okay, so at Halloumi we expect to get, say, 40 or 50% precision on the Higgs self-coupling. So I think that's pretty good in the sense that we're going to do a lot better in future. We essentially have not started measuring this thing, this fundamental property of nature. Don't forget, you know, the Higgs self-coupling, why is it interesting? The Higgs self-coupling is telling you about the local shape of the Higgs potential, right? The Higgs potential looks like this. And the Higgs is sitting here. Now this is a minimum, a turning point. So the first derivative of the potential here is 0. The second derivative, V double prime, is the mass squared. So by measuring the mass, we've started to measure the shape of this potential. The third derivative is the Higgs self-coupling. Let's call it lambda Higgs cubed, which is now starting to tell you about the local shape of this potential. Okay, so by measuring this, we're really going to start measuring the local shape of the Higgs potential. Why is the local shape of the Higgs potential interesting from a physical perspective, or special? Well, it's pretty important, right? Because the local shape of the Higgs potential determines the way that electroweak symmetry breaking occurred. So it's a pretty fundamental thing that the Higgs gives mass to all of the particles that it gives mass to. And the way that that happened is thus pretty important. And the way that happened is determined by the shape of the Higgs potential. So the current state of the universe and its distance past are inextricably linked to the Higgs self-coupling. So this is tremendously important on basic grounds. Furthermore, as many of you may have heard, this Higgs potential actually turns over at very large field values, and so the standard model could be unstable, and we could potentially, the universe could potentially decay in the far future. But if there are any evidence for a non-standard model like Higgs potential, that story could change. So not only is it fundamentally linked to the distant past and the origins of our universe, but also it's fundamentally linked to the distant future of our entire universe. So it's no small fry when it comes to big fundamental questions. So we want to measure it. And 50% would be starting to get there. It's sort of very unsatisfactory. You know, we're talking about measuring other couplings. You know, for instance, the Higgs ZZ coupling, we will measure at something like 1.5% accuracy, so there's a big discrepancy. But it's still pretty cool that we could mention it, or could measure it. What would happen, for instance, currently the central value is about a factor 3 bigger than the standard model prediction. So if imagine that persisted, then that would evolve to something like a 4 sigma discrepancy at Halloumi. So you're starting to get pretty convinced that something fishy is going on in the Higgs sector. Imagine Atlas and CMS both had a 4 sigma discrepancy at Halloumi. You know, that would be, sorry, I can't remember which experiment this factor 3 is, but one of them. So that would be pretty exciting. But it's important to do a theory sanity check when we're thinking about the future. And so, one important question to ask is, you know, if we were to see something significant at Halloumi, imagine we were to see something like a 4 or 5 sigma discrepancy, that would mean that the Higgs self-coupling deviation would have to be something like 200% or 250%, that sort of ballpark, to get 4 or 5 sigma at Halloumi. Yet, if new physics were to show up there and not somewhere else, that would mean that the UV would have to be pretty special, whatever's going on to generate to explain the microscopic origins of the Higgs sector, because it would be generating a 2 or 250% deviation in the Higgs self-coupling. Yet, if that's where new physics is going to show up, it would have to give you a standard model like Higgs ZZ coupling, for instance, at the 1.5% level at Halloumi. And so this would be a very, very special theory. So is it theoretically possible? For new physics to show up here? It turns out it is. So there is a model. Now this is something that I worked on, and as I say in my notes, I'm not bringing this up just as some form of selfless self-promotion, a selfish self-promotion. But I think this is an important question, And so with my collaborators, Ennio Salvioni and Gauthier Durieux, we studied this. And the answer is yes, but it's a bit weird. So there is a model that you can write down called the custodial quadruplet. Scalar. So it's a model where you have a new scalar field which has hypercharged, there's two of them, one is hypercharged 1/2, one is hypercharged 3/2, and they're in the fourplet representation of SU2. So one has different representations. You can think, if you're not so familiar with representations and non-abelian symmetries, it's the same thing as charge, but for non-abelian. So if you have a theory with a U1 symmetry, you can have particles like QD with charge 1, 2, 3, 4, and so on. When you go to non-abelian, those numbers represent label representations. So you can have an electroweak triplet, quadruplet, quintuplet, and so on. So this is a quadruplet. And in this model, you can write down everything completely honestly as a theorist. So you're not fine-tuning any parameters. You're not setting any interactions to 0. You write down every interaction you can possibly have. You give it an order 1 coupling. You're not doing anything fishy. And then in this theory, it turns out that the corrections to the Higgs vector, so that think of this as Higgs ZZ or Higgs WW couplings, relative to the Higgs self-coupling, scale like this. They scale like 3 times mh squared over 4 pi v squared plus mh, oh no, not squared, mh over m, which is m is the mass of this extra scalar field, all squared. So in practical terms, we know what this is. This scales like 1 over 200 plus 1 over 580 in units of the 3 TeV for the mass of this heavy scalar. So you see that the modifications to the Higgs self-coupling relative to the modifications of the Higgs vector-vector couplings can be a factor of 200. As I said, this model, I mean, if you want, I can write it down for you, but it's probably better for coffee time or lunchtime than going into the details of it now. It's a model that, as I said, only a parent could love it. It's not particularly appealing. It doesn't fit into any narrative about any of those puzzles that I wrote down. Okay, it's not, I would not defend it. I would not want it on my gravestone. But nonetheless, it could exist. It could be there. It's completely self-consistent. And so this is a theory where you could have a 1% deviation in the Higgs ZZ, Higgs WW, all the other couplings essentially, and a 200% deviation in the Higgs self-coupling. So it is still theoretically possible that new physics could show up at high luminosity LHC through measurements of the Higgs self-coupling. In other models, the more familiar ones that you're used to hearing about, 2 Higgs doublet models and so on, this would not be the case. You would expect the deviations of the Higgs vector-vector coupling to be similar to the Higgs self-coupling. So in those classes of models, it would be, for them, it would be unlikely that the new physics shows up first in the Higgs self-coupling. It would be more likely first in the other more precise ones like the Higgs ZZ, for instance. Yes?
Can I understand a little bit more what you mean by theoretically possible? Because nature doesn't care what theory says, right? Does it mean more like, so what exactly are the constraints? We constrain ourselves to a Lorentzian variant QFT with some presumably gauged symmetries. What exactly are our constraints in the theory that makes that sentence?
Yes, okay, so I'll answer your question. First, I would sharpen what you said. You said nature doesn't care what theory says. I would say nature doesn't care what theorists say, which is maybe a bit more precise. No, so yes, so theoretically possible is that essentially those 2 criteria that I wrote down, when we're in no man's land, talking about unexpected things, we still have to make sure that we're not crackpots. And essentially those 2 criteria are the not crackpot criteria. So number 1, that the theory isn't pathological, that it's a quantum field theory. You can, in principle, calculate observables and so on. It doesn't violate unitarity or something like this. And the second is that you haven't done any tricks of like fine-tuning parameters to try and get an expected result. So for instance, I can take a 2 Higgs doublet model and get a Higgs self-coupling modification that's 200 times bigger than the Higgs ZZ coupling modification, for instance, I can do that. But what I have to do is fine-tune to an order of about 1 in 200, a cancellation between different parameters to make that happen. And so I can do it, but when you have to fine-tune like that, it doesn't mean that that theory is wrong. That could happen in nature. Fine-tuning does happen sometimes. But as a theorist, we reduce our priors for that, because there would be this other layer, like why did nature know that it wanted, why did nature want us to discover new physics in the Higgs self-coupling first? If it's a standard two Higgs doublet model, it would be a bit peculiar. So those are the sort of criteria. And I haven't, and also not, for instance, setting any couplings to 0. So more practically speaking, this quadruplet, let's call it big phi, can have couplings, it's in an electroweak quadruplet representation. It has hypercharge. One of them has hypercharge half. One of them has hypercharge minus half. What I really mean in practice, what do these restrictions mean? It means that I write down, for instance, a renormalizable 4D theory where I write down every interaction I'm allowed. So I have something like this Higgs cubed. I would have things like big phi squared, Higgs squared. You write everything you're obligated to. You're obligated to write everything, and then you go ahead and calculate what this is. And if you do this for this model, this is what you automatically get without playing any games, without setting, for instance, this coupling to be super small or something like that. Does this answer your question?
Parts of it, yeah, but
We have time, so if you want to sort of probe further on this, this is...
Sure. So I get that, but I think maybe what I'm saying is when you say theoretically possible, you're sort of considering extensions to the standard model which you accept, right? And I'm just trying to probe a little more. So you've added this new gauge symmetry.
No new gauge symmetry. So this is like just you just have the standard model gauge symmetry, and you've added a new field that has some charge under those gauge symmetries.
Okay, right, okay. But then it's in some bigger triplet, so it's a different representation.
Yes.
Okay. I think I don't understand my own question well enough to probe further. I'll think about it.
Okay, but it's an important question. Like these are not trivial questions. Yes.
I have a question maybe a little bit related to this. I mean, I'm not a VM standard model guy, I'm a QCD guy. And in QCD, for instance, one of the big problems are like hadronization effects, so when you cannot describe any quantitative perturbation theory. And now my question is like, in these beyond the standard model approaches that you're considering, are you thinking about it in terms of we can compute this perturbatively? I mean, or could it also be a possibility in the sense that all of these physical observations might be non-perturbative, and you can only do like modeling or something like this?
Yes. So the most interesting BSM scenarios, in my view, are the strongly coupled ones. The sort of like QCD. So no, for me that's not a restriction. In fact, it's almost more plausible. So if the UV theory is some strongly coupled gauge theory or something like that, no, then absolutely that's something that a lot of people, including myself, consider. I write down this model, or I haven't even written it down, but it's the references in the notes, just to show you an example of a theory where new physics shows up first in the Higgs self-coupling. But in general, what would I consider acceptable BSM models to think about for extending the standard model? Any non-pathological theory. Any theory that doesn't violate unitarity is interesting. And I don't have, personally, I think before the LHC started running, we had theorists had strong priors about what's more likely, right? There were certain very fashionable theories and ones that were not. And I think what the LHC has taught us is to be as open-minded as possible. Because those very popular theories, for instance, didn't show up yet. Maybe they still will. But we have to really cast a very wide net now. And I'm trying to convince you that there's a whole load of things that could show up there, maybe not. Nobody wrote this down, right, and made this point before the LHC was running, because why would you? Like, But now we have to be open-minded. And so no, there's no restriction about strongly coupled or perturbative or anything like that. Anything that's not pathological. It doesn't even have to be a QFT. You know, there are extra dimensional scenarios where essentially the theory is becoming, you're hitting the string scale at like 5 TeV, and that's really would become string theory. There's a bit where it's described by quantum field theory, and then it would really be string theory or something like that. That's also plausible in my view. Yep.
I think you said some more towards my question.
Okay. Okay. Oh, okay. Any more questions in this point? Yep.
What is the status of fork heat coupling?
No, but it's also very, very interesting, right? Because that, like I mentioned, that's sort of like the last parameter. You know, of course, we haven't measured the Higgs-Yukawa coupling to electrons, and we won't, and things maybe at FCCE or something like this. But in any case, no, that's much more challenging. I don't have to hand the errors, but if you add a third Higgs here, which is what you have to do, then you're paying another phase space factor. So you've got another 1/8 pi or something like this. And the rate, so the rate's going down, and you're pumping more energy through this S-channel Higgs here, so that propagator is falling off. So it's very, very hard, and I wouldn't be surprised if the limits are like a factor 10 bigger than this. Essentially, no measure, not even close. Okay, I was going to show you. Just to wrap this up, could we show figure 1 just? It doesn't matter. You can, if you're interested later. I mean, this is the point in any case. So let's go on to consider my last example of unexpected, unexpected new physics. And this one is interesting because it highlights a very different sort of signature at high Lumi. And it's potentially related to the neutrino sector. For some people, the class of models I'm going to talk about are super interesting and attractive. For some people, they're not. But for me, it's interesting because the story for high Lumi and the story in terms of signature space is very interesting. So I'm going to call this section neutrinos. In this sort of suggestively, playing on the word to suggest that one might have. Okay, it doesn't matter. Don't look at the figure, right? We've moved on. It really doesn't matter because I already said it in words. Whether there could be new physics in the neutrino sector. Okay, so we're going to sort of do some simplified model building, and consider a slight extension of the standard model in the neutrino sector. So we consider a theory where the Lagrangian is the standard model Lagrangian, then you add some new states. They have kinetic terms, which you can think of as being sort of like right-handed neutrinos, but with a twist. So there's some Yukawa coupling, the lepton doublets. We're just going to imagine, for now, for simplicity's sake, just one family, okay? So imagine, or sorry, one generation. Imagine there's only one generation. H. So this would be, in normal terms, this would be like the right-handed neutrino. But then we will add in a partner to this right-handed neutrino, which I'll call just big N. So in here you have the standard active lepton doublet. So this thing has charge. This is the Higgs. This thing is in a doublet of SU2 and it has hypercharge 1/2. This guy here, this is all in 2-component notation because 4 components gives me a headache. So we'll stick with 2-component notation. So you can think of this if you're like, this is a Weyl fermion, just a 2-component fermion, or you can think of it as being a Majorana fermion. But we give it a Dirac mass with this guy here. So this is actually a Dirac state. Now you can see that this theory has a global symmetry where I rotate L and N by a phase. That's called e to the theta L. L and N. And NC goes to e to the minus I theta L NC. So you see that this theory has essentially lepton number symmetry, right? It's invariant under this global symmetry. Now this lepton number symmetry is going to have profound consequences, so keep it in mind. We also see that M, this parameter M, breaks a potential symmetry, which is like that chiral symmetry that we discussed before. You could have had, if you didn't have M, you could have independently, in addition to this symmetry, you could have independently rotated n by e to the I, let's call it theta n. Sorry. N goes to e to the I, theta n, n. Okay. So M is the only parameter that breaks that symmetry, and so we can use that to track. We call this a spurion analysis. Some of you will have heard of this, some of you not. There's material in the appendices of the notes to help you understand better. But this means that we can track effects that are related to the chiral symmetry breaking for N throughout the theory. Okay, so when the Higgs gets a VEV, so below the electroweak scale, we can rewrite this theory now as L equals L. We've got all the kinetic terms, and then I'm going to call it M0 nu NC plus M N NC. Okay, so just counting states, we know we should expect a massless fermion just by staring at this, because we have two fermions which have, let's say, call it positive chirality. There's a chiral symmetry for these two states here. This is the neutrino now, so the Higgs dotted with this has given us V times lambda, which is the mass term, times the neutrino. And so we have two with one charge and one with the opposite charge. So we can only, even though we've got mass mixing here, when we diagonalize everything, there has to be a massless fermion left over, because I can only write down one physical Dirac mass. A Dirac mass pairs a state with a state of opposite charge. So some linear combination of these two is going to be paired with, some linear combination of these two is going to be paired with NC. Sorry. In practical terms, we can just go ahead and see that. So we do a rotation. Nu n goes to just the standard 2x2 rotation, cosine minus sine of phi, cosine of phi. Let's call them mass eigenstates nu tilde and n tilde. Tangent of phi is just m0 over big M. So we do this rotation, and our new Lagrangian has the kinetic terms plus now a mass, which is the root of big M squared plus little m0 squared, times n tilde nc. And you see that nu tilde appears nowhere apart from its kinetic terms. So we've got a massless neutrino, and it's mostly, if we take little m0 to be much smaller than big M, then this this mixing angle is small, so the massless state is mostly aligned with the active neutrinos, so it has the usual electroweak couplings times cosine of theta, which is of order 1. And then we have an additional Dirac fermion here, which has mass, if this is a small mixing angle, essentially approximately just big M. And it has a small overlap. This component here, n tilde, has a small overlap with the initial gauge eigenstates. So they're coupling to the gauge fields of that field has are suppressed by sine of phi. Okay. And so we call this, we call this state here a heavy neutral lepton. Usually there are many terms that are used in the literature. This is, I think, the most common, because this thing is heavy, it's neutral, and it has lepton number. So it's fairly self-explanatory. Okay, now this theory is sort of interesting. As I said, you know, with neutrino masses as being one of the outstanding puzzles in particle physics, if one restricts to a certain type of theory and a certain assumption about couplings, then that would suggest that the particles associated with neutrino masses are at very high energies, essentially. But if we relax those assumptions, then perhaps, I mean, and I have to say that personally, but one should never listen to any theorist priors too much. So long as prior that the theory should not be pathological is a good one to listen to. But you know, I would personally think that that's probably what's likely to happen. That the physics responsible for neutrino masses is very heavy. But it's certainly possible, logically, that the mass scale associated with the physics that generates neutrino masses is light, and so there could be lepton number-y things happening at collider, accessible collider energy scales. This theory, though, as yet does not generate any neutrino masses. So we've not actually, at this point, not connected to the question of neutrino masses. All we have is some extra state lying around that is Dirac and carries lepton number. Okay, is any of that unclear? Anyone have any questions? Nope. Okay, excellent. So what is the collider phenomenology? It's actually very, very interesting. Oh, but sorry, one other thing. Because M breaks this chiral symmetry, it can be arbitrarily small. So there's no prior for where what mass scale M should be at. Because if it's the only parameter in the theory that breaks the symmetry, then the UV, the IR, anywhere, then any corrections to its mass must be proportional to M. So I could do a bazillion quantum loop calculations and see what corrections I get to this parameter M, and they all have to be proportional to M itself. You don't get additive corrections because this is the only parameter in the theory that breaks the chiral symmetry. To put it another way, if M were 0, then N would have this chiral symmetry, and you could never generate a mass for it. So there's no prior on where M should be. Okay, so it could be at collider energies. So now let's think about the collider. So this state, it carries lepton number and has a small mixing with the active neutrinos, i.e. the gauge eigenstates of the neutrinos. And what that means is if this mass big M is less than the W boson mass, then for instance the W can decay to it. So you can have processes that produce an on-shell W at the LHC. And this could then decay to, for instance, an electron and this heavy state, N, or let's call it N tilde, sorry, with a rate that's proportional to sine of phi squared. So there's sine of phi in here, in that vertex. And so the rate goes like sine of phi squared. So then this state, N tilde, can propagate for some distance. We're going to calculate it in a second, or I'm going to show you the results, sorry, in a second. And then it could decay. Now, how could it decay? The only way to decay, it's carrying lepton number, so it needs to get rid of that lepton number somehow. And so the only way for it to decay is to emit a virtual W boson, let's call it W minus star, to a lepton. Let's just consider one family again, so let's talk about an electron, and then a pair of fermions from the off-shell W, FF bar. Now this could be a lepton and a neutrino, or it could be a pair of jets. Okay, and you see that here there's no violation of lepton number, which is related to the fact that this theory has not generated any neutrino masses. And so the initial state has 0 lepton number, so the final state should have 0 lepton number, so you have to have E minus and E plus in your final state. If these two, the W here doesn't carry lepton number. So if this two quarks, obviously there's not lepton number, but if it was a fermion, charged lepton and a neutrino, that would be a lepton number 0 final state as well. Okay. Yes?
Talking about violation of lepton number and neutrino masses. In principle, a Dirac master doesn't violate lepton number. This holds only for the Uranium.
Yes, absolutely. Absolutely. So here we've not generated a neutrino mass. We could add another sterile state in and give that generate a Dirac mass for the neutrinos without breaking lepton number. I'm just saying that with this field content and this symmetry, the only way I could generate a neutrino mass without adding new fields would be to break lepton number. But yes, it's a very good clarification. Yep. Can I enhance it? Absolutely. So yes, so these, so I'm doing one family, but absolutely, if you had 3 families, then there's no need, or 2 for instance, there's no need for these couplings here and these mass terms here to be flavor aligned. So you could have this thing here, doesn't have to be like an electron flavor eigenstate. It could be an admixture of electron muon flavor. And so indeed you could get E and mu here.
And can you do this with one?
Yeah, I think you probably can. Yes, I think you can, because this here you could have lambda E L E plus lambda mu L mu in here instead of this, and probably get that.
And that could be a signature.
Yes, exactly. Yep, 100%. Any other questions? No. Okay, great. So, what does this look like? It turns out, for generic enough parameter space, it's super interesting because the lifetime, if I take the lifetime and calculate the average distance that this would propagate if it were relativistic, which it would be if it's light enough, then the average distance that this would propagate before decaying is something like 15 meters in units of GeVs for the mass, scales with the 5th power, over 10 to the minus 4 over sine squared of phi. So this, if this is the sort of ballpark, you would get, what would you see at colliders? You would see a sort of central lepton coming from one side, and then on the other side you'd see a gap, and then emerging out of nowhere in your detector, it could be the muon system, whatever, you have a positron and a pair of jets, or 2 leptons. So this is this is a displaced vertex. So this is super spectacular sort of process that you could observe at the high Lumi. Okay, we can do a sensitivity estimate. So I'm going to need a figure up in a second, I think figure 4. We can do a sensitivity estimate. So what sort of parameter space could you hope to probe? So the 13 TeV cross-section for W's, W plus plus W minus, it's not the same because protons have charge 1, so you don't produce the same number of W pluses as W minus at the LHC, is something like 2 times 10 to the 7 femtobarns. And the branching ratio of W to lepton neutrino is of order 10% if we're sort of talking about all flavors. So then we expect the number of displaced vertices that we see to be of order 2 times 10 to the 6 sine squared phi times the integrated luminosity. So we expect, if we're assuming that like one event is so spectacular, so this is a theorist estimate, one event is so spectacular that it's a discovery of new physics, that then we would expect to set a limit, if we haven't seen anything, on sine squared phi of around, it has to be less than about something like 2 times 10 to the minus 10 if we had 3,000, if we had high Lumi. Okay, so you show figure 4. Thanks. Okay, so here we go. So this is a sensitivity estimate for high Lumi. For Alice, the ones to look at here are Alice and CMS in red and green here from this reference 14. It's all in the notes. And you can see that this sensitivity estimate that I made does not do so badly. So what did I say? Something like 2 times 10 to the minus 10. This almost gets down to there. Not quite. So you're coming down to here. So a few times 10 to the minus 10. So you could get access to, at high Lumi, to extraordinarily weakly coupled new states in the lepton sector. You know, this is UE squared is just sine squared of phi in our notation. So you're going down to extremely weakly coupled new physics. And so for me, this says that there's lots of room left to explore at high Lumi. So now I have some questions for you that we're going to try and answer together. The first is, yes, please keep it up. No. So, thanks. What determines here the mass cutoff? Like how far we go in this direction? I'm not going to answer it. No, I think, so even we're going even more simply. So we're going to try and explain the shape of this curve. So I just want to know what limits how far you can go up this in this direction.
Well, first of all, you have W mass that limits.
Exactly.
But if the intersection happens at lower masses, which is the case there because it's 40 GeV, then it determines by the intersection of the upper line, the upper bound, and the lower bound.
Yes. So if you follow these lines down here, yes. But it's the W mass. If the W mass were twice as heavy, then you would expect the cutoff to be higher.
I mean that there are two parameters. Like, okay, you have these two lines in case the Bragg ratio does not depend on the original mass, and this is obviously not the case once you are near the kinematic threshold.
Sure.
So basically, these are two lines, but once you come up to the threshold, you get this cutoff.
Yes.
But if you remove this cutoff far away, then the intersection just is at some point. I mean, if you just change the W mass to infinity, the spot will look the same.
No.
Okay.
No. So W decays to 2 states here. So each of them can at most have mass. You know, you're essentially going to get about half a W mass of energy on each side. And so if I were to increase the W mass, you'd presumably be able to access higher masses. So for instance, if you do the same plot for the Z, it comes a bit further to higher masses. So that's the limit. You have at most a W mass to play with kinematically to produce these states. And so indeed, as you take the heavy neutral lepton heavier, you know, you could in principle go all the way up to the W mass and this thing would just be super soft. But then, as you said, you're essentially, the kinematic factors, the phase space is essentially suppressing you. So you expect to be around sort of, no, you're absolutely right. There are phase space factors, but you expect to, so let me say, you expect to not go beyond the W mass for sure. And ballpark less than the W mass. But no, you're right. Actually, sorry, I take it back. You know, you could in principle go to, it could have gone to 50 GeV or 60 or 70, depending on how big your luminosity is. Yep. And how far you can go into that kinematic regime. Excellent. Thank you very much. What determines the shape, like where this lower edge is? Yep. Pardon? Yes, exactly. So as you go to lighter states, for the same coupling, your displacement is just getting larger and larger. So you're losing more and more events. You're not getting them in the detector. And the upper edge. Yeah. Yes, I think that's it. So essentially, as you go to the upper edge of this line here, you're probably losing displacement. So then you need some other search. And what other factors could be at play here? So apparently, so I had an interesting bit of input from some colleagues who work on these models. And so the current search, as you can see, we're not going to go to it, but the current limits are on figure 3. And in the current limits, the sensitivity is much weaker. These are from CMS, I think. And the reason for that is that they are not including the hadronic. Apparently, they're not including the hadronic channel in here. And also, there are backgrounds, right? These are super spectacular signatures, but nonetheless, there are backgrounds. And so there are various cuts put on to reduce those backgrounds, and those cuts are reducing the effective luminosity. Okay, so I think we should move on. And yes, I wanted to come back. You're absolutely, I just want to say that you're absolutely right that it's really phase space factors that are pushing you down below exactly MW, for instance, in here. Okay. So, in any case, I'm optimistic, so I like to look at these plots, assuming that we can include all the channels and do much better. And so there's a huge amount of room to cover at high lumi. Now, the last little thing is oscillations. So, as I said, thus far we have not generated any neutrino masses, but we could with a model like this. So you can see that model the model is up there. And so there are two options for generating neutrino masses. One would be to introduce another state which has lepton number -1, and then you could have Dirac masses, or you can break a lepton number. There are many ways to do this. You could have terms such as n squared, delta C, n c squared, or even a Yukawa coupling that's breaking lepton number. You can see that here, this term breaks lepton number, whereas that term didn't because you had L and NC. All of these will generate neutrino masses. Let's consider this one here. Once you've included this breaking of lepton number, what you see is that you've broken lepton number, so everything essentially becomes a Majorana. And what you get is that this Dirac heavy neutral lepton gets split into two Majorana states that are very, very close in mass, and that splitting depends on delta C. So essentially, you're generating a Majorana mass for everything now. And what this means is that you also, or another consequence is that you no longer have lepton number as a good symmetry. So when you produce a state in, for instance, a lepton number eigenstate, so for instance, or a gauge eigenstate, moreover, the states that propagate are the mass eigenstates, and they're no longer lepton number eigenstates. And so you can have, just like you have neutrino oscillations, you can have heavy neutral lepton oscillations. Essentially, in a very similar way, it's actually entirely analogous, essentially, to standard neutrino oscillations. So in those diagrams that I wrote before, you could produce this state here, but then it could oscillate into effectively an NC, thanks to the lepton number violation, and lead to a spectacular signature, which would be that, I can write it like this, I just got now a Majorana mass insertion, that now you could have something like E minus, N goes to an effective NC, it's no longer a lepton number eigenstate, and then here you could have a W plus off shell. So you would have E minus, and then a plus charge final state here, which would be super spectacular. You're getting huge, sorry, not huge. You're getting a lepton number violation in the final state, but the standard model respects lepton number. So you would have, I mean, in some region of parameter space, you would have something really, really bizarre looking, right? You produce an electron centrally, and then somewhere out in the detector, you produce another electron displaced with a pair of jets or some other leptons. And so this would be very, very spectacular. I don't want to spend too much more time on this. There's a limit on, actually no, we can leave it there because I think I should probably move on. So anyway, so this is a sort of quick overview of one class of models which could be connected to neutrino mass generation. You see, once you have these terms switched on, you generate a neutrino mass. That bounds the parameter space a bit, which we could discuss afterwards if you're interested, and gives rise to signatures at the LHC, which are high luminosity LHC, which are very, very spectacular, and for which there's a lot of parameter space which is still uncovered. Okay, are there any questions about any of that? Yes?
Yeah, to just see in specifics, you only need to see the three right particles, FF and E+. But for identify lepton number violation, you need to also see the initial electron and how feasible it is to connect the displaced vertex to some lepton originating.
It's a really good question, and it's beyond my pay grade. So all I can say is that so it's sort of like as the events become more and more busy, how do you connect what to what? And I think that that you can, because a lot of papers have been written about this. A lot of people have thought about it. I think you can. I think a lot of the noise is QCD. So in terms of counting, if you just looked at your event after the fact, so you've got your displaced vertex and you've got your event on tape, and you say, what is the lepton number in the final state of this entire event? Even if there's other stuff from pileup, then it would still violate lepton number, unless you've misidentified leptons, which I think is a part of a potential background. So yes. What I should say though is that already, you know, if you're already seeing in the part of the parameter space where you have displaced vertices, if you're already seeing displaced vertices, it's already new physics, and the lepton number story is really the piece of information that would tell you, it's already clearly new physics, sorry, is the piece of information that would tell you that this is potentially connected with neutrino masses. I think you can also have prompt. You can be in parameter space for this where you're not displaced, and the prompt searches give you access to the final state. And here, these heavy neutral lepton oscillations are really key in seeing it, because the signature is no longer displaced. It's just a lepton number violation in the first place when you go to larger mixing angles. Any other questions? Nope. Okay, excellent. So that was, we're doing well here. That was everything I wanted to say about unexpected. So of course nobody can tell you what unexpected things are going to show up at high Lumi, but there's a huge range of things that could. This was 3 samples, the Higgs coupling to muons, the Higgs self-coupling, and this story with heavy neutral leptons. There's sort of interesting signatures. High Lumi does very well on all 3 fronts, and really opens up a huge amount of parameter space that remains to be covered and is relevant, as I hope to convince you, even in the case of the Higgs self-coupling. But we don't know what to expect, and I think we should never forget the muon. All right, not all discoveries are precursored with someone saying, well, here's an outstanding theoretical puzzle, and so we're going to see this, and then it shows up. Sometimes things just fall out of the sky, and the muon was one of those things, and we still, if we're honest with ourselves, don't know why it's there. So we should always be open-minded. Any exploration is worthwhile, even though you don't know exactly where you're going. Okay, are there any, on that broader philosophical point, are there any comments or questions before I move on to the lecture week scale? Nope. Okay, excellent. So the second half of these lectures is concerned with the other reason, and for me, probably the strongest reason to expect new physics to show up at high Lumi, which is that the lecture week scale is special. And it goes back to this point that I made at the start, which is that we don't really have the why of lecture week symmetry breaking. We have the how. We have a phenomenological model which does is incredibly successful at making predictions that we can test with colliders. But we don't know what the origin of that lecture week sector is. And so now I'm going to say, I mentioned when I was talking about superconductors, I mentioned that there's also an analogy with pions and QCD, which I think some of you are familiar with. So now I'm going to sort of lean into that analogy a bit and talk about it, because one of the main classes of potential UV completions to this Higgs sector of the Standard Model that I want to focus on is really a class of UV completions where the Higgs sector of the Standard Model really is like pions. Okay, so there could be some UV completion, which it might be strongly coupled, it doesn't have to be, where the Higgs is essentially composite. But actually there's a broader, I'm going to try to define more broadly what a pion-like Higgs would be, and we can discuss it. So just for a reminder, I'll discuss pions a little bit. Okay, so we have the UV and we have the IR. For our purposes here, this is QCD and what's known as the chiral Lagrangian. In the UV theory, we have the important degrees of freedom are the quarks, QQ bar, and the gluons. There's, of course, the leptons, the photon, things like this, but for QCD, these are the ones we're going to focus on. And there are parameters, right? There's alpha strong and the quark masses. As we go to the IR theory, we have a whole slew of particles. We have pions, rho mesons, the neutron, the proton, and the parameters that we observe are things like m pi, f pi. F pi is the pion decay constant. We'll discuss that a little bit later. Things like m rho, all of the parameters of related to the hadrons that we observe, and everything can be calculated, right? If you have a powerful enough computer and enough friends who are good at programming, you can calculate all of these, the particles that you should expect to see, and their parameters, the masses and interaction, decay constants, things like this, from this fundamental theory. Okay, and that's what we hope to have for the electroweak sector. Does anyone have any questions about this? Nope. Okay, excellent. So I want to focus more closely on the pions. Okay, so we have 3 pions. We can call them pi 0, pi plus, and pi minus. Or equivalently, we can call them pi 0, pi 1, and pi 2, where pi plus is 1 over root 2, some linear combination, pi 1 plus I pi 2, and pi minus would be the conjugate. The parameters we're interested in, we have the m pi 0 is 135 MeV. M pi plus minus is 140. And so this is quite suggestive, right? The masses aren't identical. Sorry, my 5's not very good. The masses aren't identical, but this is suggestive that these 3 pions are sort of coming as a family in a sense. They're coming packaged together, right? If one of them was totally different mass, like say 50 MeV or something like this, then you wouldn't have that suspicion. But this is strongly suspicious that there's some symmetry going on that relates them. And in fact, there is a symmetry, so we're not going to do this in detail because it's not super relevant for us, but if you have questions about it, I can for sure talk about it. But it turns out that a good way to think about them is as particles that emerge from the spontaneous breaking of an SU2 cross an SU2 symmetry. You might be familiar with this in terms of chiral symmetry breaking, and in that case you would package them. Again, we don't need to go into this in detail, but just maybe for the slightly more theory-oriented folks here, you can package them into some, we'll call it a big pi state, which is known as the nonlinear representation, where should I go this? We'll come back to this actually. We can come back to this tomorrow. It'll be more useful to do it then. Okay, so But nonetheless, this is suggestive that there's some symmetry that relates all 3 pions together, that they somehow come packaged together. And so when we look at the mass term, for instance, you could write the mass term as being the same for all of them. Pi 0 squared plus pi 1 squared plus pi 2 squared. And so this would, if we write down this term, we can say this respects a symmetry. We can think of this symmetry as actually, one way of thinking of it as being like an SO3 symmetry. You put 3 of these in an SO3, in a triplet of SO3, and you do a rotation on them. This term stays the same, okay? But that would predict that the masses are all identical. But then, you see, we can start to think in a sort of model building theory driven way. You could say, well, that the overall the mass is SO3 symmetric, and then there's some small breaking of SO3 symmetry, which generates a mass splitting that deviates the masses between them. So we can think, so to first approximation, to order better than 5%, we can imagine that there's an SO3 symmetry relating them, or equivalently an SU2 symmetry, which is the truth of the matter, but we'll come back to it. And also we see that this mass term, it respects an SO3, but breaks a shift symmetry. So for instance, if I were to shift one of my pions, let's say pi 0, goes to pi 0 plus a constant, then this term is no longer invariant. Whereas the kinetic terms, that enter the propagator, for instance, d mu pi squared, you can see that these respect a shift symmetry. If I shift the pion by a constant, pi 0, sorry, by a constant, you see that the derivative hitting a constant just gives you 0. So the kinetic terms respect a shift symmetry, whereas the masses break the shift symmetry. Okay, but then, so we could start to understand that these masses could be arbitrarily small because they break a symmetry. This comes back to this spurion jargon that I mentioned before. Because if I just had the kinetic terms like this, they would never, there's a half, they would never generate any mass term for the pions. Because if they just have the derivative like this, because this respects a shift symmetry, so at no level, 5 loops or something like this is something that breaks that shift symmetry going to be generated. So that means that then we expect that the pions can be naturally light, we would say, because the pion mass, if it were 0, it wouldn't be generated just from this kinetic term alone. Okay. And this is we're gonna come back to where the origin of this shift symmetry in a bit. However, we have to remember that there's QED. And so this is not the whole story, this kinetic term. In fact, the kinetic terms look like this. We have that story for the neutral pion, but for the charged pions, we have the gauge interactions, i.e. a mu pi plus all squared. And so the fact that the charged pions are charged actually changes the theory very dramatically, because this term here, it does two things. Number one, it breaks this SO3 symmetry because it treats the charged pions differently from the neutral pions, this coupling here. And it also breaks the shift symmetry. The shift symmetry that would have acted on, say, pi 1 and pi 2. If you recall, pi 1 and pi 2 make up the charged pions. Okay, so we're building up slowly our understanding of the low energy theory. I can actually bring this up here. And so, as we're starting to learn, in an effective field theory, and this is an effective field theory, right? We've gone from the UV in principle, imagine we'd only built colliders that operated like 200 MeV. We would have discovered the pions and not much more regarding QCD. So we would just have these ingredients to work with. We would see that there's a neutral pion and two charged pions. But we know that there is a UV completion. After the fact, we know that UV completion is QCD. But in principle, we know that there had to be a UV completion, and it could have been anything. And in that UV completion, we can, in the effective theory, we can study the symmetry structure and start to make guesses about the nature of that UV completion. Now, one guess that you could make is that there's nothing to forbid a term in the theory that modifies the mass terms that looks like this, something like h bar e squared over 4 pi squared, giving a mass, let's call it lambda squared, to the dimensionful parameter lambda squared to the charged pions. There's no symmetry that can forbid this, because we saw that this charge, this term here, breaks the SO3, because it treats the charged pions differently than the neutral pion, and it breaks the shift symmetry. So there's no way, whatever the UV completion is, I can't forbid this term from arising, where lambda is the mass scale associated with the UV completion. Okay, so this is the logic. And this, I really mean mass scale here. This object here is dimensionless. You've got a couplings, but you've got an h-bar. Okay, and so we're sitting in the IR and we're trying to make guesses about the UV. So we're staring up and trying to figure out what's going on. And one obvious thing to do is you could say, well, this is the only term I see in the theory that could generate a mass term that actually splits pi 0 from pi 1 and pi 2. And so these corrections that you would expect to be there, whatever the UV completion is, perhaps they're responsible for the mass splitting. Or one can even turn it on its head, and we'll come back to this. If lambda were too big, if lambda were, yes?
If you broke all the symmetries and then also you said that this is an IR theory, then in principle you should have started with the Lagrangian containing all the terms. Like the only thing that you need to worry about is Lorentz invariant.
Yes. Yes, so that's all there. Absolutely, yes.
Yeah, so why would you need to generate this term if it's just there by definition?
No, absolutely. So indeed, so that's, I mean, it's two faces of the same coin, in the sense that because you have this, you can't not have this. That's what I mean by generated. I'm not meaning that like microscopically it's generating it, but you're.
Why would they be related at all? Why do they need to be related?
The mass splitting and this. So absolutely. So yes, very good point. So they don't need to be related. But suppose the mass scale of the UV was like TeV. Then this would generate a mass splitting that's way too big, right? The charged pions would be like 100 GeV or something like this. So this is the logic. So we can't. So I think your question introduces the next step of the chain of the logic, in the sense that you can't forbid this. This is what you expect from the UV. So what are the implications? And so if E were 0, then if E were 0 and the charged and neutral pions still had a different mass, then there would be some source of SO3 breaking in the UV, and you can make guesses about that as well, so you know it's there. But what we're doing is taking the ingredients that we see and saying, what's the absolute minimal number of contributions that we have to have, and we can't avoid this one. Does this answer your question?
At least one contribution
100%. Yes, exactly. Exactly. So we at least have this, but there could also be, let's call it delta L, and this is a really good point, UV. There could be additional contributions, which is just say, let's call it m tilde squared, pi plus squared. That could be entirely just coming from extra braking that's beyond the electromagnetic gauge coupling. And this is important. I'm going to come to these straight away. So, nonetheless, so we measure that m pi 0 and m pi plus have a mass splitting which is like 5 MeV. So whatever the story is, once we have L equals all the other stuff, let's call it L0, plus delta L, let's call it QED, plus delta L UV. Once we have all of this, in the end of the day, the mass splitting is 5 MeV. And so one could have, there are two options. One could have lambda, much, much bigger than the GeV scale, and then fine-tune delta lambda QED against versus delta lambda UV. So you could do that. You could have that those UV, those extra contributions are cancelling this to give you a small mass splitting. Or you could say no tuning, in which case lambda would have to be roughly less than or equal to something like 750 MeV. The reason for that is if you just put the numbers in here, and you put in if this mass is 135 MeV squared, and you put this in with 750 MeV, I think it's 750 MeV, you generate a 5 MeV mass splitting. So these are the options. So you either have, and this doesn't mean, by the way, if you take lambda less than 750 MeV, it doesn't mean there aren't additional UV contributions, but it just means they're not fine-tuning. You don't have big ones cancelling each other to give you a small number at the end of the day. So this is known as the sort of the naturalness strategy. If the theory isn't fine-tuned in the UV between different contributions to give you a small number, what are the implications? And this is the implication. Are there any questions about that? Anything that's not clear? Or yep.
Yeah, so a question like how you build these contributions. I can think of a contribution that has a form beyond pi and mass squared divided by the new scale. Like you have some loops and the heavy physics runs in the loops. So lambda would be the denominator. Here is the numerator. How do you choose between these options?
So indeed, you should have contributions like this, where you have, say, pi, this thing to the 6th power, and then lambda would be in the denominator.
No, I just talking about the case that you mentioned previously when you had v left divided by lambda squared. Like
Yes.
Here you can also write pi and mass squared divided by lambda squared, and then just pi and
So yes, so good question. So but the whole thing has to be dimensionally commensurate. So if we have big lambda in this is a good question. If we have big lambda in the denominator, let's call it 1 over lambda squared, then the rest of the thing has to have dimension 6. Because it's a Lagrangian, so it has dimension 4. So if you have big lambda in the denominator, you could have something like m pi squared pi to the 4.
yeah, I mean pi and mass to the 4th and pi and to the
Yes, exactly. You can have that indeed. That's exactly right. So you should write down everything consistent with the symmetries, and this is one such term. So pi m pi to the 4 over with pi squared. So this thing here.
yeah, okay. To put it in the context.
So that should be there. You should include it.
To put it in the context. Right now I'm thinking about why pions do not acquire a contribution from Higgs event. So this is because of Higgs only
Well,
appear in some loops and their scale appear in the denominator.
Yes. So they do because they get their mass from the quark masses, ultimately. which comes from the Higgs VEV. But that's sort of besides the point. Your question is a good one. So you should have everything. So you should have terms like this, and the terms like this do exist. But the point is that if you have, this is already telling you that lambda, you see, if you were to bring lambda, for this to be big, lambda, for this to be important, lambda would have to start to be close to m pi. And then you shouldn't be using an effective field theory because you don't have a scale separation. So if you have a scale separation, by definition, if you're using an EFT, you have to have a scale separation. And if you have a scale separation, then this is, you can write it like this, lambda squared pi squared. And so this is a number that is by definition much smaller than 1. So it's a small correction.
Yeah, okay. Let me try to formulate. So you, using your logic, you concluded that if there is some new physics, it should be below 750 MeV.
Thereabouts, yeah.
We know that there are the bosons. So just applying this logic, you started with no assumption on UV completion. You derived that the requirement lambda there should be less than 750.
Yes, yes.
So you can exclude the bosons because they do not fit in this logic.
Excellent. Yes. Okay, I understand your question. No, that's a very good point. So indeed, so it's telling us that in the UV completion, the new physics shouldn't lie too far above a GeV scale. It should be around the GeV scale. But then it also is telling you that then you're jumping to the next UV completion, which is the electroweak sector at 100 GeV, and it's telling you that there should be a comfortable scale separation. It's the same logic again. There should be a comfortable scale separation between the physics that generates the QCD scale and the electroweak scale. Otherwise, this indeed would be the electroweak scale. How that's implemented here is that there is no such thing as a pion above the QCD scale. It's now a pair of quarks. And quarks have chiral symmetry, and so they can naturally be light, which is why ultimately why the pions are light. So indeed, you're jumping up to the UV completion of the UV completion.
So I don't know beforehand what is the
Yes.
I just want to complete the theory, and
Yes.
they complete this theory. So it's also UV completion. So
Yes.
my question: when do we choose this lambda squared, which grows with the energy scale, and when should we avoid this behavior because it would lead to some?
So this is we're working with the effective field theory, and we don't yet know what the UV completion is. And this is telling you, and so you don't even know that the W and Z exist yet. And this is telling you that there should be something at 750 MeV or less. It's not telling you that there isn't something at higher energies as well. That's the logic. So there should be states in the UV completion at around 750 MeV. Or to put another way, this effective field theory should break down pretty quickly by around 750 MeV. But that doesn't mean that there isn't, the Planck scale and lots of other higher energy scales. It's more the logic goes the other way. It says that at least by a GeV, the theory is breaking down. There should be new states. Great question. Okay, so I'm going to wrap up. We started a little bit late, so I'll just finish a little bit late. But these are great questions. So nature had two options. One is that actually there is not new physics below like 750 GeV or so. And what that means is that whatever the UV completion is, it's most likely going to be fine-tuning a UV contribution, something that's not calculable or estimable within the IR theory, against the QED-like contribution because there's some parameter that we see breaks the SO3 symmetry and the shift symmetry. So it could have been fine-tuned, or it could have not been fine-tuned, in which case the new physics would have to kick in. It turns out nature chose this option here. And actually in the chiral-Lagrangian, in QCD, you can calculate this contribution. And when you calculate it, you can calculate or estimate pretty well, the charge-neutral pion mass splitting. And it comes out at 3 H bar E squared over 4 pi squared m rho squared. You know the rho meson. A1, that's one of the another one of the vector mesons. M rho squared plus m a1 squared log of m A1 squared over m rho squared. And indeed, if you put in their masses, which are around the 750 MeV ballpark, you get the 5 MeV, mass splitting. And so the hierarchy problem of looking at the parameters in the IR theory and which symmetries they break, and then what are the unavoidable contributions based on symmetries, unavoidable contributions to the low energy parameters from the UV theory. One could have already said that there would be something like the rho meson. Yep.
If we didn't know the answer, so if we didn't know the UV theory, could we choose among those two options?
In principle, yes, right? You could have had, you could have imagined a different UV completion where, and I'm sure it would be an interesting exercise, but not a trivial one, I don't think, where there's this contribution and some other contribution, and you can't tune them to cancel each other. You could, in principle, do it to give you a small answer. It's not impossible. And in fact, we do see some from the IR perspective, some weird fine tunings, like related to the masses of various nuclear states, things like this. Even something slightly not relevant here, but it's astronomical, right? The one example of a fine tuning we see in nature is that the angular size of the sun is very close in mass, or it's very close in scale to the angular size of the moon. So during a solar eclipse, the sun just blots out the moon, and that enabled us to confirm, for instance, GR because of the light from we could see the light bending from stars and so on. So tunings do happen in nature, and that's why people refer to the hierarchy problem in modern, these days, really as a strategy. It's like the hierarchy strategy or naturalness strategy, because it's a way of making guesses if the UV isn't tuned, but it is logically possible that the UV could be tuned, and I'll discuss that with regard to the Higgs. Any other questions? Nope. I think then probably. Oh yes, and so this is what nature chose, and then what the next layer is, which I think comes back to a question that you already asked, is that okay? Then we can write down QCD. But actually the question of how light the pions are, so the pions get their mass from the quark masses. If the quark masses were 0, you would have an exact SU2 cross SU2 chiral symmetry that's spontaneously broken, and the pions would be really, apart from up to this coupling, the pions would be Goldstone bosons, and so they would have been massless. So their leading mass contribution comes from the quark masses. And so then the question of whether or not the pions could be light, even once you get above QCD, it remains. And the way that question is answered is that actually the quark masses can be naturally small because they break a chiral symmetry, as we discussed already. Yep?
That quark mass, for example,
yes.
At the top quark mass,
Yes. Yes.
So it is sufficient that just one of the masses is small, just one of the parameters that breaks that symmetry is small, or do they have all?
So yeah, no, it's an interesting game. So now you're getting into the sort of the vacuum structures questions of QCD. So if the top quark, you get a top quark bound state in nature. You can have it, but the binding energy it's coming from the gluons. So it's of order the QCD scale. So a TT bar state is to a first approximation just a top and an anti-top, and QCD is irrelevant. Largely, it's not totally irrelevant, but largely irrelevant. Then if you get, in terms of the mass of the state, then once the quarks become lighter than the QCD scale, that's the reason you get the pions. Because then when the quarks, the quark mass is a small parameter compared to lambda QCD. And so in the UV theory, you have a chiral symmetry which lets the light quark Yukawas be small, which means that then multiplied by the Higgs Vev, the masses become small. And in the IR theory, that's reflected because your expansion parameter essentially becomes m quark over lambda QCD. And indeed, well, it's actually square root of m quark over lambda QCD or something like that. And indeed, that's the reason that the pions are lighter than the rho meson and everything else. We'll come back to this, but that's why they're light. And so as long as you have some quarks, And you can call them what you want, right? The label is irrelevant. As long as you have some quarks that are lighter than the QCD scale, you would get pions. But you would get states like pions. But if you had, say, 3 light, all of them light, I mean, it's already a good approximation to treat 3 of them as light. But if the strange was also like 4 MeV, you would really have had a full set of 9 pions and so on. And if you had more light quarks, you would have more pions and so on. Any other questions? Yep. This MA1? Yeah, so that's just one of the vector resonances in QCD.
But why should I expect that the mass splitting is proportional to the vector mesons and not the spin zero mesons?
That's a very good question. That's a really, really good question. I think, when you do this loop, I think what you have is something like, I don't know how to do a double-lined one. I can't remember, but I think it's like this. And it's related to the fact that there's essentially like rho photon mixing in a sense. But no, indeed, you would expect it to be of order the general mass scales in the theory. If you calculate all of the one loop contributions, you get one of them, the dominant one you get is this. But I would bet that your intuition is right and that the masses of other hadrons will also enter at some order in this contribution. Probably. That would be my guess, but I don't want to say it for sure.
The diagram that you lines are the raw and the A1, no?
No, there has to be a photon because it's E. So it's somewhere there, but I'm not sure. Don't look at this too hard. For A1, no, I don't know. I think, yes. Also, this isn't even gauge invariant on its own. There would be like one with a 4 vertex and things like this. Any other questions? No? Okay, let's leave it there and we'll see you tomorrow.